Deoxyribonucleic acid, or DNA for short, is the molecule that carries the genetic information in all living organisms. In terms of structure, DNA is a polymer that's made up of four subunits classified simply as A, C, T, and G. There are three principal components in each of these subunits: a unique nitrogenous base, a phosphate group, and a sugar. They bind together through their phosphate groups to form these long polymer chains, which are the bases of DNA. The order of the subunits is extremely important, and it's how the genetic information is stored. It gets a little more complicated though, because DNA isn't just one chain. It's actually two, and they're held together by interactions between the nitrogenous bases. This interaction is known as the hydrogen bonding, where A likes to pair with T and C with G. This hydrogen bonding, along with various other intermolecular forces, twists the DNA into its distinctive ladder-like structure known as the double helix. This is not how DNA looks in the cell though. It's associated with a whole bunch of proteins that are super small in volume packed together. It gets tighter and tighter progressively until we eventually get something called a chromosome, which is the smallest structure of the DNA base that you can see under a typical microscope.
What's cool is that it's actually possible to separate DNA from pretty much any living thing. Hi, I'm Cyrill as LIBRES, a second-year chemical engineering student from Technological Institute of the Philippines, Manila. And for this video, we will run an experiment to extract DNA from any fruit, in my particular case, banana, with things that may be readily available at your home.
In terms of materials, of course we will need a banana. We'll need some dish soap, table salt, and isopropyl alcohol as well. Before we get started with the main process, there are other couple of things we need to do first. The isopropyl alcohol will be used later on, but it needs to be ice cold, which I will explain later why when we use it. I measured that about 80 milliliters and then I put it in the freezer. We also need to prepare a soapy salt solution. To do this, mix about 120 milliliters of water, 15 milliliters of dish soap, and about a teaspoon of salt. Ideally, the soap to be used must be both uncolored and unscented, but it's okay to use one that's not, but this could impact the impurities present in the final yield. What we're doing here is making a so-called extraction solution that we'll be using to get DNA out of the cells. For now, it's going to be temporarily put on the side, but when we use it in a few minutes, I'll explain exactly how it works. Now we can get to the actual process. I cut and peeled bananas that were moderately sized and then shoved them all in a plastic bag. This could have been a zip bag, but I don't have any, which is fine. Just make sure to work extra careful so the solution won't go anywhere and be a mess. It's time to squish all the bananas in the bag. By doing this, we are exposing as many of the banana cells as possible. We're structurally destroying them as well. This crushing step is very easy to do with banana, and it's a major reason why I'm using them. DNA extraction from other items such as chicken liver or peas is popular, but they don't fall apart just as quickly and often. You'll always need to use a blender. Things should be sufficiently broken up, so it's time to add the soapy extraction solution from before, then mix it around and try to break up any left bits. Mixing it gently and not creating bubbles as much as you can is crucial, so you're sure that the soap is actually in direct contact with banana cells. It doesn't really look like a lot is going on here, but it's the most critical step in extracting the DNA out of the cells. This is the general anatomy of plant cells that bananas are made of. The three main things for these experiments are the cell wall, cell membrane, and the nuclear membrane. The cell wall is a rigid sugar layer that's usually made up of cellulose, and the other membranes are made of things called phospholipids. The DNA is contained in the nucleus, so to get it, we need to break all three of these barriers. The cell wall that was destroyed when we mashed banana was the first one to go. This exposes the cell membrane that is made up of phospholipids, and as I said, the phospholipids arrange themselves into a bilayer like this, where the polar heads are on the outside and the non-polar tails are shielded on the inside. Soap itself is somewhat similar to phospholipids, where it has a polar head but it only has one non-polar tail. The structural difference is minimal, but in water, it causes soap to form spherical structures called micelles instead of these bilayers. Even though they form this very different and distinct structure, they're still similar enough that they want to interact with each other. As the soap is added, phospholipids and proteins begin to be blocked from the membrane of the cell and inserted into its micelles. Often, to some degree, the soap molecules can inject themselves into the membrane. This eventually leads to severe damage to the lipid bilayer and make it structurally unstable. The membrane bursts open with more squashing and the contents of the cells are spilled out. This opens the nuclear membrane, which is the last thing to get through, and it's just like the cell membrane. The soap messes with the lipid bilayer, causing it to burst, and the DNA is released. Although the cells are only spitting out DNA, since it stays dissolved in the water, we do not actually see it in here. As I've mentioned in the intro, the DNA is tightly packed and associated with lots of different proteins. Many of the proteins have positive charges which interact with the negative charges of the phosphates in DNA. It is for the purpose that we add sodium chloride. The sodium ion can come in and neutralize the charge. It will also help the DNA strands to stick to each other in clumps large enough for us to see. We now need to filter off all the solids from banana junk. This is carried out in 2 steps. First, get rid of the very big pieces through a strainer and then through a coffee filter to get rid of the smaller stuff. But if you have no coffee filter available with you like me, you can use a tea bag. By emptying the tea bag, you should be left with the paper itself and you can actually use it to filter out the solution. This part is very slow, so some patience is needed. Once everything passed through the filter paper, we are now ready to isolate the DNA. To do this, get the ice cold isopropyl alcohol from earlier. We chill the alcohol so we can increase the yield of our DNA as alcohol is more effective in precipitating DNA when at low temperature. Because of its immiscibility to DNA is increased, and so is to cut the precipitation processes. Dump all of the alcohol in. Very quickly, there's a bunch of this white stringy stuff floating to the top, and this is the DNA. However, there are likely to be several proteins that also precipitated out. You should be able to mix things and wait until all the DNA floats to the top. After several minutes, you can finally collect it and do whatever you want with it.